Okay. I don't know if these are ever not going to start awkwardly, but I know these first few are. So I might as well smooth over that by directly addressing it. Also, for these first few, I'm going to point out that these are intended to be a supplement for the book, not a complete replacement of it. The book goes into much more depth and has much more details. My idea here is mostly to give a brief summary, try to highlight some of the most important terms, though not all of the important terms, and work out a couple of problems by hand where I can sort of explain my reasoning. There will occasionally be sections where there's not as many problems to work out, like, say, this one, because there are a couple of sections that are very conceptual. But I do have a problem I can do from this one, and I can do the rest of the stuff, like highlighting the basic ideas of it. So, diving in from there, that is the most horrible section marker I have ever drawn. But we're starting off with section 2.1. So I mentioned this in the last video, I believe, but the first chapter is a brief run through of pre-calculus. So if there's anything that you're not sure you remember from pre-calculus, if there's anything that's giving you trouble on the placement exams, chapter 1 in this book is the place to look for it. But for what we're talking about here in this class, we're starting with 2.1, which is a little bit of an oddity, kind of. We're going to touch on something here that we're then going to put aside for a whole nother chapter. Because it's sort of motivation for what we're going to do the rest of the chapter, which is something called limits. Now, I'm going to mention limits as we go through here, but most of this chapter is about the concept of rates of change. And it's sort of a bridging concept from something you did in pre-calculus, which was average rates of change. So we're clear on where that's from. I'm not going to write that out every time. To one of the things that is kind of the big topic of calculus, though it usually goes by another name, which is instantaneous. Is it? It is. It does have two ands there. But it has... There we go. I can spell sometimes. So calculus, one of the big things in calculus that you'll probably have heard of, the derivative, is giving us the instantaneous rate of change. So this sort of serves as the bridging concept between these two classes, pre-calculus to calculus. Again, like I said, the rest of the chapter we're going to sort of veer off and talk about something called limits, because you can't actually talk about the instantaneous rate of change without talking about limits. But they did want to go ahead and start off with this bridging idea. Right? So in pre-calculus, we had this average rate of change. If you recall that was the change in y over the change in x. That was sometimes written as delta y over delta x. Delta in calculus generally means change in. If you're trying to read it out loud, you might as well read it that way. This was also sometimes called delta f over delta x, where f is the name of the function in question. And really, you could put any letter there, because any letter could be a function name, as long as it's not x. That one's generally reserved, at least in calculus. And the other thing that you might remember from pre-calculus is that this average rate of change was the slope of the secant line. Right, so just to give a brief visual example, if you have 2 points on f of x here, then this guy, this straight line, is a secant line. Right, so the average rate of change between this point and this point gives you the slope of the secant line between them. So in calculus, this instantaneous rate of change we're talking about is, well, the main problem comes in with that change of x on the bottom here, right? So instantaneous means that there's no change in x. So delta x equals 0, and right away we can see that that's a big problem because we're not allowed to divide by that. Well, we kind of are. That's what limits are for. So the way that we'll wind up writing this down, though we'll use some slightly different language when we get to it, is like this. So that's what limit means, is that we can't divide by 0, but we're going to have to come up with some tricks for dealing with that, and we'll go more into that a little bit later on. But just to continue this sort of mirrored concept idea, is that this instantaneous rate of change, something that you, again, may have heard of before. Sometimes these ideas from calculus trickle down to general knowledge, which is that the derivative is the slope of the tangent line, and since the derivative is related to this instantaneous rate of change gives us the slope of the tangent line. So same sort of idea. Right. So that's the basic idea of this section. The section talks a lot about velocity, and it sort of points it out here like it's something special. It's just a rate of change. So it's the rate of change of position with respect to time. And that's all it is. They use it as an example in the book because it's something that has a specific name. It's something that comes up a lot, especially if you're taking calculus to do physics, which I know is a big reason why a lot of people take calculus. But it's just sort of a very, very common example of a specific type of rate of change that has a name. Right, so we can talk about, or you probably did talk about in pre-calculus, average velocity. That's how fast were you going on average. In calculus, we'll talk a lot about instantaneous velocity. Because anytime you see rate of change in something, you can just replace it with velocity and know that you're talking about a specific type of rate of change. So that's the basic description. So the problem I have to work out is how do we find this idea of instantaneous rate of change? And the problem is that we can't find the instantaneous rate of change yet. We'll be able to, but we can estimate the instantaneous rate of change for f of x equals 1 over x plus 1 at x equals 0. Right, so when you have a problem like this, it's kind of a word problem. It's got a number of words in it anyway. Sorry about that. I will figure out how to make this sound stop so we don't get interrupted again. So the first thing to note there that we could also get from what section it's in, we're going to be estimating it. Right, so that's a key thing to look for to try to tell you what type of process to use. Right, so in this case, we've only really got the one section, so hopefully it's a process that shows up in there. But if this were to show up, say, on the homework that covers up a couple sections, right, there's going to be a difference between estimating, which means you'll want to use a process like we use today, and finding, which means you'll want to use a process like, okay, so it's not going to be on the homework because the process would be something we learn next chapter. Well, we might learn it in the next couple sections. Anyhow, if it said find the instantaneous rate of change, then you would want to find it exactly, right, and know for sure. Since it says estimate, we're going to be using stuff from this section. Of course, instantaneous rate of change is some sort of key idea of what we're doing, right? It sort of identifies what type of problem it is, hopefully hints to us that it's from this section, even if we weren't doing it in a video about this section. And then we have sort of the information that's specific to the problem, right? So that first line that I have up there, that's going to be the same if I'm asking you this type of question, no matter what the question is, right? I could ask you this type of question 6 times. That first row would be the same. The stuff that you plug in comes from that second line. So our process for this estimation is going to be to find the average rate of change over 0, and this 0 comes because of what this says, right? So because this says x equals 0, we're going to start over 0 here, and then let's call this A. Oops. So we're going to let A get smaller and smaller, right? So really we want to find the average, and I'm putting quotation marks there with my hands even though there's no video involved with this, or video of me at least. So we're going to find the average rate of change from 0 to 0. That's what we'd really like. That's what instantaneous means, is that the moment we start, the moment we stop are the exact same moment, right? That instant that we have there of 0. But we can't do that because, like we mentioned up here, we can't divide by 0. Right? So what we're going to do is we're going to divide by a number that gets smaller and smaller and smaller. So first, let me actually have the problem on the screen. We're going to find it over, let's say, 0 to 1/2. Right? So in that case, we want to find the average rate of change. If we recall, that's delta F over delta X. So that's F 1/2 minus F of 0. 1/2 minus 0. Now, just to help folks recall, right, this is something from pre-calculus, but just to help us remember, it doesn't matter what order I put the 0 and the 1/2 there as long as I'm consistent, right? It could have been F of 0 minus F of 1/2 divided by 0 minus 1/2, since they're both the same, right? So the order doesn't matter as long as it's the same order on top and bottom. F of 1/2 means that I need to plug 1/2 in up here. F of 0 means that I need to plug 0 in up here. And then 1/2 minus 0 is just 1/2. Now, that looks pretty horrible. But one of the nice things about dividing by a fraction is that that's the same thing as multiplying by its reciprocal. Really, dividing by a fraction, the fraction part wasn't necessary. Dividing is always multiplying by the reciprocal of the denominator. It's just when the denominator is a fraction, the reciprocal makes a little bit more sense. So the first step that I'm going to do is I'm going to change that dividing by 1/2 is the same thing as multiplying by 2. Right? Because 2 is the reciprocal of 1/2. So dividing by something is the same as multiplying by its reciprocal. So dividing by 1/2 is the same as multiplying by 2. So I can rewrite this as 2 times 1 plus 1/2 is 3/2. So I can simplify that a little bit. 1 over 1 is just 1. So there we go. Already looks so much simpler. Right? We still have a complex fraction there. And I don't know about you, but I hate complex fractions. They're the worst. I want to get rid of them as soon as possible, especially if I'm trying to do some algebra with this. So I'm going to use that exact same trick. Right? So dividing by 3/2 this time is the same thing as multiplying by 2/3. So I'm going to take this 1 and multiply it by 2/3, and then subtract 1. 2 times 2/3 minus 1. Now I need to subtract some fractions, which means I need to get a common denominator. So that 1's going to become 3 over 3. It's just a usually meaninglessly complicated way of writing 1, but in this particular case, it's very helpful. So we get 2 times negative 1/3, negative 2/3, which, for reasons that will become clear later, I'm going to turn into decimal form. Right? So that's 0.6 repeating. The little hat on numbers means that you keep repeating those forever and ever. So that just means repeat 6s until you've drawn an infinity of 6s, which I don't have time for. So the other thing you could do is just plug stuff into your calculator. Like this is algebra. I'm working this one out in depth. We're going to do 2 more of these, and I'm not going to work them out in so much depth. So if you got really bored watching that and you sped up and you're just tuning back into the video right now, good news, we're not going to take that long for the rest of them. I'm going to use the exact same tricks. I'm just going to do them quickly and without commenting on them. And I do want to point out there's also no problem with just plugging this into your calculator. As long as you're careful about how you plug it in, you can go for it and do that all you want, right? So that is our average rate of change, where we have A being 1/2, right? And really, I don't know, this is not the way it should be. It shouldn't be getting smaller and smaller. It should be gets closer to 0, right? And this is a 0 here for the exact same reason there was a 0 above, because it was part of the problem, right? If we wanted to find the instantaneous rate of change for f of x equals 1 over x plus 1 at x equals 1, we would do the exact same thing, except for we would have a 1 here, 1 instead of a 0, and we choose a number close to 1 there, which 1/2 is still pretty close to 1, right? But now we need to do this getting closer part, right? So we could really pick any number that's closer to 0 than 1/2 is. We could pick 1/3, we could pick 1/4, we could pick 2/7 if we wanted to be just wild and crazy about it. I have chosen, in the work that I have done ahead of time, to do 1/10. No particular reason. Again, like I said, you could pick any number there that's closer to 0 than 1/2 is. So when we find the average rate of change there, like I said, I'm not going to do all of the details, or I'm at least not going to explain out how fractions work over and over again. But I'm going to use the same tricks. Here I'm doing that multiplying by a reciprocal thing. And get to negative 10/11, which, as it turns out, is negative 0.90909090909, and so on and so forth, which we represent by just putting that bar over the 0.9, because that's just going to keep repeating forever, right? So far we've gotten two numbers, and our whole point here is we want to try to find a pattern, right? Maybe I shouldn't have buried the lead quite so hard, and I should have mentioned that earlier, but the whole idea of getting closer to 0 is we can't actually make it get to 0, but maybe we can get enough steps along the path that we know where it's going to, right? We can't watch it get to its final destination, but maybe we can figure out enough that we know where that's going to be anyway, right? So 2 is not a great number to get a pattern, but 3 sometimes is. So again, you could choose any number here that is closer to 0 than 1/10 is. I chose 1/100th. That's pretty dang close to 0. And the closer you pick it to 0, the closer your final answer is going to be, right? So that's the idea here, is that the smaller that difference is, the closer we're going to get. So let's do this. All right, so we got our formula for the average rate of change there. We can flip that denominator by using the multiply by a reciprocal rule. Oops. Go ahead and plug that in. All right, we do the reciprocal rule again. We do some fraction subtraction, which I'll admit is kind of fun to say. And then we multiply, and then we figure out what that is. And this time it turns out need to go a while before it starts repeating, but it's going to keep doing 9900, 9900, 9900, 9900 ad nauseum, right? So at this point, it seems pretty clear to me what this guy is getting close to, right? So we have negative 0.6, negative 909, negative 990099. And it seems pretty clear that we're getting close to negative 1. Right? So that's our estimate. That's our guess. That's our assumption that the instantaneous rate of change is probably going to be negative 1. So like I said before, this is an estimate. We didn't find it. We don't know what the instantaneous rate of change is just by looking at these three numbers. But it seems like a more than simply educated guess to think that it's probably going to be negative 1. And that's about all the problem work we can get from this one. This one was, as I mentioned at the start, a very sort of conceptual idea. It introduced a lot of vocabulary. It's sort of introducing this idea that bridges us from pre-calculus to calculus, this idea of going from average rate of change to instantaneous rate of change, and sort of picking up this idea of limit along the way, and even introducing that notation of limit. And then for the rest of the chapter, we're going to be talking about what limits are and what sort of ways do we have to actually solve them, right? Because this process that we went through right here, it may not have been too bad to do it 3 times, but to be really certain of what we're doing, we would need to do it more and more, and even then, we'd still just be making an estimate, right? So it'd be really nice to have tools to be able to figure out how to solve them, not just estimate them. And that's what we'll be doing for the rest of the chapter. So I'll see y'all next section.